In progress.
Hello friends. In the last lecture, we have seen static characteristic of the system in which we have seen accuracy, precision, repeatability, reproducibility, hysteresis curve, static error, what is range, what is span, and in today's lecture, we are going to see what are the dynamic characteristic of the system. So let's start. In this video, we will learn dynamic characteristics, speed of response, bandwidth, fidelity, measurement like dynamic range, dynamic error, and settling time. Why we learn dynamic characteristic? Why we learn dynamic characteristic? To understand how system respond over time. To design stable, accurate system, to minimize error during transient, to compare and optimize the system to ensure safe and reliable system. In static characteristic, we have seen that the system characteristic, we will not consider that characteristic as the with the concept of time, but here in dynamic characteristic, we are considering characteristic with respect to with the study of time. So, what are the dynamic characteristic? Dynamic characteristic refers to how a system or device respond to changing input conditions over time. It's commonly used in engineering, control systems, and electronics to describe performance under non-steady conditions. It tells you how fast, stable, and accurate a system reacts when input changes. So, dynamic characteristics are nothing but characteristics which are studying consideration of time. In static characteristic, we were not considering the concept of time. So, how fast and accurate will a system respond when there is the input is constant changing of time. Now, another dynamic characteristic is the speed of response. Its ability to respond to sudden changes of amplitude of input signal. Speed of response refers to the time taken by a system to react to an input or change in conditions. When we apply input signal to any system, the we get output immediately. In some systems, we don't get output so immediately except ideal system. But actually, for the understanding, we can say in some system, we are getting output late due to lag, due to delay. So this is the speed of response of the system. It is the time a sensor takes to detect and report a change in measured parameter like temperature or pressure. Usually speed of response measured in milliseconds or second. A faster speed of response is usually desirable for real-time or precise control system. In control systems, there are so many systems like underdamped, overdamped, critically damped, etc. So all are classified on the basis of speed of response. If system is moving so fast, it is known as a critically damped system. So here we can see the curve of the system where we can understand what is rise time, what is peak time, and what is settling time. Here blue line is denoted as a system response, and this is the final value of the system. The yellow line is denoted as a rise time, the purple line is denoted as a peak time, and the green line is denoted as the settling time. Here we have taken oscillatory system. So we have to understand that the concept of peak time is only understood when we have waveform kind of graph. Here, what is rise time? So how our system initially respond to reach its final value. So it is known as a rise time. Okay. So from 10% to 90% to the final value. It's for general system. And for 0% to 100% for ideal untamed system, how system respond to reach its 90% or 100% value is study is known as a rise time. Rise time indicates how fast a system initially responds to a change. It's still crucial in evaluating the speed of response and performance of control system circuits and sensors. So what is peak time? Now, peak time is the time system takes to reach its maximum value. So here is the peak time of the system. So we have to understand that the peak time occurs after the rise time, only relevant in underdamped system like those who oscillates. It is important for assessing how much the system overshoots before settling. Peak time helps evaluate the quickness and stability of the system's initial reaction. It's used in designing systems to minimize overshoot and improve control. So now settling time. It is time taken by a system to be within its steady state value. Smaller settling time, higher speed of response, the more stable system is. Here we can see after reaching to the peak time, the value falls down and comes to its final value after oscillating. So this value is known as the settling time of the system. When you give an input, it might go up and down at first, but eventually settles down near for a fixed value. The time it takes to enter and stay in that narrow range is known as a settling time. As fast settling time is, the system will give you quick response. Here we can see the graph of settling time. Okay. Here we understand the tolerance band, the concept of tolerance band, because the oscillatory, after oscillating to the peak time, the system don't directly goes to final value, but it fluctuates. So it is denoted here by the tolerance band. Here red line is denoted by tolerance band. It is showing plus or minus 2. What is bandwidth? Bandwidth is nothing but simple words range of frequencies. We all know what is waveform. So waveforms, the range of frequency is known as a bandwidth. So it is very important concept in communication. It is a range of frequency within a given band that system signal or component that process effectively. It's measured in a hertz. We all know. Higher frequency minus lower frequency is equal to bandwidth. Now fidelity. It refers to ability to follow instant by instant the variation of measurement with the time. Fidelity is the most important concept because it refers to how accurately a system reproduces or represents the original data signal or process. The higher the fidelity, the more accurate and faithful the representation of the original signal. However, maintaining high fidelity can sometimes require more resources like bandwidth, processing power, or storage. What is measurement lag? We all know that when we apply input to any system, output is not directly proportional to input, but it will take some time to show the output. So this is known as a measurement lag. We have seen the example of thermometer where detecting hot temperature, it will take some few seconds to show it to the display. So this is measurement lag of the system. It is delay in occurrence of the output signal due to its input signal. Okay. Next, dynamic range. What is dynamic range? It is a range of signals where the measuring system is likely to respond faithfully under dynamic conditions. We have seen in a previous lecture what is range and what is span. So it was all good for static systems where the input was not moving with the time. Dynamic range is the range of input signals over which the measuring system or instrument can respond accurately and reliably under dynamic means changing conditions. Dynamic conditions means system is responding to signals that are changing over time, not just static inputs. It is range of signals which the measuring system is likely to respond faithfully under dynamic conditions. In short, when input are changing over time, the output is also changing over time. So study of this range of any signal or any system is known as a dynamic range. Dynamic error. In static error, we have seen the error is equal to difference between indicated value or recorded value to the true value. But in a dynamic error, there is a minor change that input is changing, constantly changing. So, dynamic error is defined as the algebraic differences between the indicated value and its true value at any instant when measured is a function of time. In static error, the measured was constant. They describe how measuring system behaves when the input is changing with the time. A good measuring system needs to respond correctly and quickly to these changes. So, error means nothing. The difference between indicated value and its a true value with respect to time. So, in today's lecture, we have seen dynamic characteristic of the system where we have seen speed of response, rise time, peak time, settling time, dynamic range, dynamic error, measurement lag, etc. And in next lecture, we are going to see errors of the system. What are the errors, gross errors, random errors, instrumental errors, etc.